All right, thank you so much for the introduction and the invitation to speak at this great online hybrid workshop. Yeah, so I decided to speak about, I guess, this preprint that's mentioned in the abstract. Trying to prepare something a bit more circle method related, but it wasn't quite ready in time. So we'll talk about this instead. And yeah, apologies if some of you have seen me give a talk on this recently, for example, at the IIS, but I think that maybe the audiences haven't overlapped so much. So with that, yeah, in fact, I'm actually going to structure the talk by starting by reviewing a bit of what we know about moments of L functions, mainly in higher rank situations. And then I'll kind of transition to talking about this result concerning bounds for standard L functions. So just as a bit of notation, I'll always write Q for the analytic conductor, at least approximately, of something. So more precisely, of the elements of some family of automorphic forms that I'll call F. I'll write L of pi s or L of s pi for the L function. I'll spend some time talking about integral moments of L functions, which are, of course, a tool often used to bound them. And K will denote the, I guess, half the exponent. And occasionally, just when talking about some of the available results in the literature, I'll refer to the cuspidal variant of one of these moments, which means what you get by, I guess, viewing this 2kth power of the standard L function as the second power of the twist of that L function by an Eisenstein series, and then allowing yourself to replace the Eisenstein series by some fixed cusp form, that kind of thing. So is there any question about just what the notation we have, or anything else on this slide? Okay, so I guess there's a standard heuristic for when one expects to be able to estimate a moment of a family of L functions, at least assuming the available technology is there concerning trace formulas or large sigma inequalities, things like that. And the heuristic is basically, well, you open things up using the approximate functional equation, maybe focus on the part that doesn't involve the root number for now, and just look at the lengths of the sums. So you need the family size to be, I guess, sufficiently big in order to expect, after something like a trace formula, for there not to be any off-diagonal contribution to the sum, meaning the sum over the family should just detect the diagonal condition. And that happens precisely when the family is a bit bigger than q to the k over 2, where q is, again, the analytic conductor of the pi's. And you can translate that in terms of the exponents to a familiar condition, which says that the degree of the moment should be at most 4 times this logarithmic ratio of the family size to the analytic conductor. And I guess kind of when you have equality there, when 2k can be exactly 4 alpha, that's sort of this threshold situation where you might expect to be able to say something non-trivial, just barely as far as moment asymptotics are concerned, maybe by solving a shifted convolution problem, for example. And so I'll refer just in the next few slides to this range where 2k is allowed to go up to 4 alpha inclusive as the primary range. And we'll see some examples that'll be very familiar that will kind of focus this. So the simplest example would be if we take our family to be the one relevant for studying moments of the zeta function, say in a dyadic window. So here the family size in some sense is something like q, and the conductors are, again, all about size q. So the ratio between the conductor and the family size is 1, this exponent here, which tells you that the primary range is when the exponent in the moment goes up to 4. And we know this from the history of the subject that kind of moments lower than the 4th moment for zeta are kind of easy to understand asymptotically, whereas the 4th moment we have for something like a century, and then the higher moments we don't know how to understand asymptotically, unconditionally at least. And I guess one direction that people have looked is, they've looked at maybe larger families where the conductor is not so big compared to the family, where you can actually study higher moments. So one example that's been studied a fair bit is when you take all the Dirichlet characters modulo some modulus lowercase q in some dyadic range, say indexed by uppercase q, and maybe you will also allow t to vary in some short window. And so then for something like this family, which has size something like q squared, the primary range would now be up to 8 rather than 4. And indeed, people have kind of successfully over the years been able to chip away at higher moments. So Connery, von H, and Sound understood the 6th moment asymptotically, and then more recently Chandy and Lee the 8th moment. I guess here they don't quite get a power savings asymptotic, so it's not quite as satisfactory as it is for zeta, corresponding to the fact that this family maybe isn't quite as complete, isn't quite as good at detecting orthogonality. So there are some difficulties that remain there, but you see there is this phenomenon that you can evaluate higher moments for these families that are bigger in terms of their conductor than zeta. Okay, so for the rest of the talk, we're going to transition to examples that concern automorphic forms of higher rank. And we'll start with families that are kind of quite big. So the biggest possible family is the one I've indicated here, where we have all of the cuspidal automorphic representations for GLD. I'm just going to focus on the spectral aspects, so I'll take everything to have level 1 in this talk for simplicity, so GLDZ rather than say a congruent subgroup or working adelically or something like that. And then we'll ask that the analytic conductor, this product of the numbers that shows up in the functional equation, be of size roughly Q. So here I guess one can show that the family size is comparable to the dth power of Q. And so the primary range now goes up to 4D, which of course gets bigger and bigger as D increases. So in principle, by taking D sufficiently big, there should be a large number of arbitrarily large moments of families of L functions that maybe there's no good reason why one could not evaluate them asymptotically. This hasn't been done as far as I know. I mean, in fact, for this particular family, I think things have only been understood rigorously when D is 1 or 2. Okay, and when D is 2, it's kind of more by analogy to the literature, but it should be kind of something like that should be available. So for say D3 and higher, something like this is open. And I mean, I think it's an interesting question to actually just look at this question, take D very large, maybe even start by taking the degree of the moment rather small and just see if you can evaluate, say, the 28th moment of some family on GL 1,000,000. That's an open question at the moment. So proceeding from this family, we're now going to shrink down to somewhat smaller families, but still on GLD. So here I should maybe emphasize that you might ask, what about the T aspect for GLD? What if you want to vary the parameter, the argument of the L function, the thing that I've called 1/2 so far, rather than just the automorphic representation? So in this situation, variation of that argument is kind of built in because you can always replace pi by its twist by determinant to the IT, which has the effect of shifting the L function of pi in the argument by IT. So the twist is kind of built in here. This will have the effect of changing the central character of pi. So for the next slide, we're going to restrict to pi having trivial central character. And I guess a similar discussion would apply if we restrict to any given central character. So in other words, we're going to work on PGLD rather than GLD. We'll still require the analytic conductor to be in some dyadic window. And so now I guess you have a slightly smaller family. It only grows like Q to the D-1 rather than Q to the D. So the primary range is a bit more restrictive. There are a couple of results. So for when D is 2, I guess the relevant moment is 4. That's the threshold range. This is exactly the moment that, for instance, Michel and Venkatesh study in their paper on subconvexity when they solve it for GL2. And then there is one result for arbitrary D here, I guess now for the cuspidal variant of the problem by my former PhD student, Subhajit Jana, which is unsatisfactory in that the moment that's considered is of a much lower degree than the range that one expects to be, feasible. I guess these numbers 2D and 4D-1, they coincide exactly when D is 2. That's the Michel Venkatesh case. So Subhajit basically generalizes Michel Venkatesh's argument to higher degrees, and what it gives is something kind of modest that grows with the degree, but is not quite as large as the threshold. So that's another open question to try to inch away at that gap between 2D and 4D minus 1 and still prove an asymptotic formula. And I should mention, I mean, these are all asymptotic formulas with power savings that one can get in these setups. Any questions so far about anything we've said here? Trust you guys in the audience can hear me okay. And yep. Okay, cool. So now we're gonna focus further. So I guess these conductor families are, I mean, these are even maybe the most interesting families from the perspective of open cases of the subconvexity problem. But now we're going to kind of focus in on families that we've been able to study a bit better, that are less interesting for those cases, but still relevant for maybe the generic cases that we now understand better. So we'll start with dyadic families. And by this, I mean, we'll take everything on GLD with no restriction on central character, with the property that the D numbers that I've called mu1 through mu D that show up in the functional equation. So the mu j's are the shifts in the gamma functions that show up when you write down the Archimedean factor for the L function. That's the notation. We're going to ask that this D tuple of complex numbers lies in the rescaling of some fixed compact set by some large number T. So omega, I've taken it to avoid all of the hyperplanes where at even one of the coordinates vanishes. So the way we should understand this condition is that each of the mu j's is in some large dyadic window, more or less, maybe between tj and 2tj. That's a good model example. And then T of course will let tend off to infinity. And when we do that, well, the analytic conductor is just the product of these numbers basically, which will be of size T to the D. The family size we can read off from something like the Weyl law for GLD, and it'll grow as indicated, and it ends up being the D plus 1 over 2th power of the conductor in the situation. So the primary range goes up to twice D plus 1. That's the range where, it's the analog of the 4th moment of zeta. Equivalently, it's the range where if you can actually do an asymptotic formula with a little bit of amplification, then you can get a subconvex bound as a consequence. So there is one result we have. I mean, I guess maybe certainly something. Yeah, I mean, I guess when D is 1, this is again just the 4th moment of zeta. But for large D, there is one result we have, which was in this paper that I wrote with Akshay Venkatesh a few years that got published last year, where we don't quite treat this moment, the 2D plus first moment, but what we treat is more like the cuspidal variant. So something like the second moment of some cuspidal twist. But we actually only treat that after passing from automorphic forms on the general linear group to some compact quotient that kind of behaves like the general linear group. So for example, some unitary group for which the analog of this is actually compact. And moreover, the estimate is ineffective. It relies on Ratner theory. So we don't even get like a logarithmic savings. We get a little O of 1 savings in the error term. So there's kind of no hope to, improve upon that result with amplification to get something like a subconvex bound. But at least it's some moment where we can evaluate it asymptotically. And I think it's a very interesting challenge to try to refine that to a more effective asymptotic formula. So the simplest example would be you could take the family on, GL2. It would then be a 6th moment of a big family, or you could take the family on GL3. It would then be an 8th moment over one of these big families. And that's something we haven't understood yet. Any questions on that while we have it up? Okay, great. Well, yeah, if you think of any questions or you want me to go back to slides, feel free to interrupt. I'm happy with interruptions. But if not, let us then proceed from dyadic families to what I'll call short families. So by short family, I mean something like asking that each of the mu j's, as on the previous slide, lie in some short interval where, okay, I've taken the interval to be of size maybe t to the epsilon, where epsilon is arbitrarily small, but maybe think of delta as being kind of like 1. So something like an interval of size roughly 1. And yeah, all of the TJs I'll take to be of the same size, maybe size T. And, just for simplicity of describing the family, I've assumed here tacitly that the TJs are well separated by T. So under this condition, yeah, the analytic conductor will of course be T to the D, just roughly the product of these sizes. The family size will be, ignoring delta, pretending delta is roughly 1, it'll be roughly like this, T to the D choose 2, which is the D minus 1 over 2th power of Q, the analytic conductor. Yeah, I guess without this condition of well separatedness, there's a natural way to enlarge the family by kind of increasing the spacings a bit, or maybe describing things in terms of symmetric functions evaluated at the μj's, such that the family size remains exactly as I've indicated here. So I haven't displayed exactly how you'd enlarge the family, but there is some natural enlargement of the family that would have the same size even without this condition here. And the results I'm about to describe will be valid without that condition for those enlarged families. So, well, in all cases of a family of size as indicated, the primary range will now be up to twice the quantity D minus 1. And so, for example, we might like to evaluate this kind of moment asymptotically. That's a natural challenge, which might be doable. So it hasn't been done yet, but it's kind of right at the threshold range. And of course, if you're interested in the subconvexity problem, there's an easier thing than moments of L functions that you could try understanding, which is instead you could look at moments of, say, smoothed dyadic sums, more precisely the ones that show up when you write down an approximate functional equation for one of these L functions. So, to get subconvexity, by the convexity bound, you can kind of just focus on the dyadic sums of length close to the square root of the conductor. And so one way you can try to study those is, well, you can look at moments of those dyadic sums, maybe smooth through something. And you could try amplifying those as well. And then this is something that's been done. So I guess Vaniach did this in a paper in Krell some time ago, 30 years ago or so, when D is 2. This was, I think, the spectral growth of automorphic L functions for, I think that was the name of the paper. Blomer and Butkin had a preprint in 2015, published just a couple of years ago, that does this for D equal 3 under some assumptions. And so then finally last year, I have a preprint now that does this for general D, not quite in the exact language I've indicated here. I'll explain the translation in a few slides, but I proved something that morally is like an asymptotic evaluation of a sum like this, yeah, I guess like in the previous cases, one can amplify and then use to get subconvex bounds for L functions, assuming they lie in families kind of the indicated shape. So I guess I'll just pause on this slide just to state the actual results one gets that way. So for example, if pi is something on GLD, let's say of level 1 for simplicity, and each of the parameters is of size T, then you get a subconvex bound. This has been mentioned, I guess, in some of the earlier talks in this conference. So, it leaves open the case when all of the μj, or at least one of the μj, is much smaller than the others. So this is a case where, we saw this talk on the work of Kumar, Malasham, and Singh, where for GL3, they can shrink one of them down to T to the 3/4 plus delta, for example. So that's not covered by this result. What you could get from the method would be like a shrinking like that, but like not specified, meaning, some exponent probably bigger than 3/4. Well, certainly much bigger than that for GLN. You could do a little bit of shrinking of them, but kind of not, it's not something that one, it's certainly not like something that is actually written in the paper, and it's not something that one can that one has any hope of kind of shrinking all the way down. To put it another way, I guess you could probably prove a theorem like this just by inspecting the proof, where you don't have the condition that each mu j is of size t, but what you get is a bound of this shape, assuming that each mu j is at most t, and with maybe a different exponent than what I've written here, this 1/12d to the fifth. So I guess the point there is that the bound you'd get that way would be trivial unless all of the mu j are more or less close to t. Otherwise, it would follow from convexity. Okay, so that's what I wanted to say about that. And yeah, I mean, there's a version of this for level. You just kind of put in the square root of the level, and then you get a bound that works for things of arbitrary level. So in particular, you get something like a t aspect bound for things on GLD. And yeah, of course, there's a lot of history on this problem that I haven't really even scratched the surface of here. But yeah, you know, many people have worked on subconvexity over the years. Yeah, any other questions just on the statements of results so far? If I guess I'll pause for a bit, but if not, I guess the plan now is I wanted to talk a little bit about the proof of the asymptotic evaluation of these kinds of moments, which is what powers these subconvex bounds. And then, yeah, that'll be most of the talk, and I'll kind of speculate a bit at the end on how one could possibly hope to refine that evaluation to study actual moments of L functions rather than the approximations to them that are relevant for subconvexity. That'll be the plan. Yeah, any questions about any of that?
Yeah, I just wanted a clarification. So
Sure.
your pi is not necessarily spherical at infinity?
That is correct. The infinity type of pi is not constrained at all. So
not a Heck mass cast form of weight zero in an IISc.
Absolutely not. So I mean, so as you know, like these things, like L infinity in general, you can write as a product of like gamma R's or gamma C's.
Yeah,
these kind of
okay.
things, and there's no constraint whatsoever on the infinity type. It doesn't even need to be tempered, for example. That's also allowed. Yep.
Okay, thank you.
Yep, thank you for your question. Any other questions before we kind of dive in a bit more? Okay, so if not, yeah, so I guess, you know, from some kind of big picture perspective, the only real tool we have for saying anything rigorous about L functions in this number field setting that we're kind of tacitly restricting to is the theory of integral representations. So I've indicated here like the basic identity that powers a lot of that, which is, well, okay, we'll take pi to be some automorphic representation for GLD plus 1, sigma for GLD. I'll write V and U for vectors in those representations. So V and U are now automorphic forms. They are functions on, for example, the quotient of GLD plus 1 of R mod the same thing of the integers, or the same thing for GLD, which satisfy some eigenfunction conditions that are described by the parameters of pi and sigma under both the Heck operators and some differential operators at the infinite place. So these are infinite dimensional representations. You know, for example, you could take pi and sigma to correspond to Moss forms, and then you could take V and U to, well, be the Moss forms that lie in those representations. More generally, you could take things of, say, higher weight in some sense that are not K invariant, they're not spherical, or you can work with general smooth vectors. And so kind of sphericality things won't really show up in our discussion here. So for general vectors and in general pairs of, let's say, cuspidal automorphic representations, you can write down this integral of their product over the common domain, GLD of R mod GLD of Z. I mean, here GLD is kind of the upper left block of GLD plus 1. And the basic identity that powers what we know about L functions is that L functions show up as a factor in a formula for this integral, where the other factor is some local integral, meaning just involving Archimedean data involving the Whittaker functions attached to these automorphic forms. So this Z of VU is the kind of thing that, if V and U were Moss forms, you would apply Stade's formula to evaluate this exactly in terms of a big product of gamma factors. But more generally, it's just some integral of some smooth functions that, give some number that shows up here. So, for example, the way people prove that L functions are holomorphic or entire is they write down this integral. And then, for example, if pi and sigma are cuspidal, I guess the left-hand side always converges absolutely. So that thing will be holomorphic once you start varying anything, like if you vary these things by twisting them. So the main point then is to know that you can actually choose vectors so that the zeta integral, this local integral Z of VU, is non-zero. Because this identity expresses the L function as this integral of automorphic forms divided by that zeta integral. And if you're going to divide by that zeta integral, you need to know that it's non-zero in order to know that it doesn't introduce a pole for the L function. So that's kind of the bread and butter of proving holomorphy of L functions. One also gets the functional equation from identities like this using automorphy of the automorphic forms. So one of the ways one can use such integral representations to study L functions is you first prove all the basic properties of L functions this way, and then you write down an approximate functional equation, expand in terms of Dirichlet series coefficients, and use, say, your favorite summation formula, like the Kuznetsov formula, to understand averages of those coefficients. Another way is, that many people have used by now, is that you can actually study L functions and their moments or estimates for them directly in terms of this relation. And so that's what we'll do. I don't know that it's so different in power from the techniques based on the approximate functional equation, but at least for what I'm describing, like the way that I know how to understand it at the moment is in this language. So you can imagine that if you want to, for example, bound an L function using an identity like this, you would want to be able to choose vectors for which this zeta integral is not only non-zero, as would be relevant for establishing holomorphy, but is moreover quantitatively not very small. And on the other hand, if you're taking spherical vectors V and U, well, Stade's formula tells you that this zeta integral here is a product of gamma factors, which Stirling's formula then tells you is actually exponentially small as soon as pi and sigma have any kind of interesting ramification. So again, spherical vectors are not really the right choice. And that kind of motivates the next slide, which is based on this paper that I wrote with Akshay Venkatesh that I mentioned a few slides ago, and also one of my follow-up papers kind of expands on it, where we identify a class of vectors that is like extremely well suited for plugging into integral representations like this and producing vectors for which these local integrals are like quantitatively not very small, and moreover for which the vectors have some kind of sensible symmetries that characterize them. So that's what the next slide will be about. I want to talk a little bit about microlocalized vectors. I should say this will be a little bit of like a heuristic and formal discussion, but my aim will be to kind of convey the basic idea that hopefully will be kind of illuminating and give some useful picture if anyone wants to learn more about this approach to the problem. So as far as notation, I guess I'll now take pi to be something on GLD, but really this is all just local stuff going on at the real place. So we could actually, it doesn't need to come from automorphic forms. It can be any irreducible unitary representation. I'll assume that the parameters of pi, the shifts that show up in the L function at infinity, are all of size and most t. I will write O pi for the set of d by d matrices whose eigenvalues are mu1 through mu d. And now, I mean, to be actually accurate, so coming back to your question, this definition is only really the correct definition if pi comes from a Moss form, so that these mu j's are all, let's say it's a tempered Moss form, then these mu j's would all be real numbers. In general, you have to tweak the definition a little bit. I just haven't written the tweaking. I mean, the idea in general is, these mu j's would, for example, come in pairs of imaginary numbers that both have kind of the same imaginary sign, and you want to negate the signs of one of them before plugging it into this formula. But maybe for simplicity, let's pretend pi comes from a Moss form. So then you have d real numbers here, and O pi would be the set of d by d matrices with those real numbers as the eigenvalues. So OPI is at least close to what is often called the coadjuvant orbit attached to pi. Coadjuvant orbit refers to the fact that it's kind of natural to think of this as living inside the coadjuvant representation of GLDR. This is the representation you get by, well, first taking the adjoint representation of GLD on its Lie algebra, and then dualizing that representation so that you now act on the dual Lie algebra, the space of functionals on the Lie algebra. I've just described it kind of very concretely here in terms of matrices for the sake of presentation. So this coadjuvant orbit, it often is. And what do I mean by orbit? Well, I guess under conjugation, very often, for example, if all of the eigenvalues are distinct from each other, this will actually be an orbit for conjugation. In other words, it'll be a conjugacy class of matrices. So it'll be the conjugacy class consisting of all matrices with a given characteristic polynomial. More generally, it's pretty close to a conjugacy class. I mean, in fact, if one did, and one maybe should, insert the adjective regular before matrices. So a regular matrix is one whose characteristic polynomial is the same as its minimal polynomial. In other words, its minimal polynomial has degree D. Then this would again be a conjugacy class. And that's kind of the way to think about it. And these coadjuvant orbits, as I'll refer to them, these OPi, they control many features of the representation pi. So for example, there's something called the Kirillov character formula that writes down the character of the representation. So in other words, the trace of a group element acting on it, as a Fourier integral defined in terms of the coadjuvant orbit. I wasn't going to go in that direction for this talk. Instead, I'm going to present another way that coadjuvant orbits govern properties of the representation, which is through what we've indicated here, these microlocalized vectors. So here's where it kind of becomes a bit more informal, but okay, let's try to parse this. So given an element tau of the coadjuvant orbit, and I didn't write this, but I'll assume that tau has size comparable to t in magnitude. We're going to attach a class of vectors in the representation that we'll refer to as being microlocalized at tau. And what this condition means is what I've written here, and this will take a little bit of time to unpack, but I mean, let's just read through it first. So pi is a representation that acts on this vector v. We can act by the group element x of x, if x is a Lie algebra element, so I guess x would be a d by d matrix. And we ask that this be approximately a multiple of the vector v, where the scalar that shows up is e, so e to the 2 pi I of the trace of the matrix product of x and tau. So this is saying in some sense that the vector is at least approximately an eigenvector under the action of exponentials of Lie algebra elements, or equivalently, I guess we could say group elements whose distance from in the Lie algebra case origin, or in the group case identity, is quite a bit smaller than t to the negative half. So it's we're kind of really zooming in a fair bit on the identity or the origin. Yeah, so we have some kind of approximate eigenvector relationship under such elements. Now, I mean, what maybe isn't obvious until one has kind of spent a lot of time working with such representations and playing around with this condition is that, yeah, there will always exist vectors of this general shape. So I don't know if you've seen the work on quantum unique ergodicity by Lindenstrass and company, you might know that this proof makes use of something called the microlocal lift of a Moss form. And so that microlocal lift gives an example of a vector that satisfies some condition like this. Usually it's not expressed this way, but one could write it this way. And so more generally for any group, or for example, for GLD, one has some notion of microlocalized vectors that have some symmetry property like indicated here. So before we go on, are there any questions about what I've said here so far? Okay. So if not, what I've written here is kind of a refinement of this first condition. It says that, in fact, elements are quite a bit bigger than what I've written here. So Lie algebra elements of size little o of 1, so almost kind of in some kind of fixed region, provided they centralize this matrix tau, one will also have this approximate eigenvector relation. And you can motivate by thinking about kind of like how this relation changes if you translate both the vector and the matrix tau by the same group element. So if you translate the vector and you conjugate the parameter tau, this relation will again remain valid kind of for formal reasons. So particular, if you translate the vector by something that centralizes tau, that's kind of what this condition says about x of x, you'd expect to get it back another vector satisfying this condition. And it turns out you can kind of diagonalize the actions of those vectors, and in an irreducible representation, they're already diagonal, and the eigenvalue is given by the same formula. So we have some class of group elements which contains all of the group elements within roughly a bit smaller than t to the negative half of the identity, as well as any group element that's just a bit smaller than 1 from the identity, but it has to centralize the matrix tau. I mean, this centralization condition, if you haven't thought about centralizers of matrices recently, you might think about the case where maybe tau is a diagonal matrix with distinct entries. In that case, the set of matrices that centralize it are just the diagonal matrices. So, the space of such X would be d-dimensional in that case. And another example would be if tau is, say, a nilpotent Jordan block, then again, this space would be d-dimensional. So it's always d-dimensional, but it might look a little bit different depending upon kind of the Jordan block structure for tau. Okay, so what can we do with this condition? Well, one thing we can do is, in part to make it rigorous, we can think about it in terms of integral operators. So there's a natural function that one can write down on the group GLD, a smooth compactly supported function, that has the effect that when you apply it to the representation, meaning you form the integral operator that you get by integrating this function that I've called omega tau against the representation. This will now give an operator on the representation. This operator should be something like a projection onto V satisfying the above conditions. So I haven't written the formula, but we can figure out what the formula is just by staring at the conditions. So we look at all of the group elements we get from either this condition, so x of x where x is of this form, or this condition, x of x where x is of that form. You kind of look at the part of like the group elements you can get by multiplying together some bounded number of such things. It'll be this region near the identity in the group that we described just a couple minutes ago. You consider something like a smooth bump function that's kind of like a smooth and indicator function of this collection of group elements. And then you weight that smooth indicator function by the inverse of the eigenvalue that shows up in this relation here. So then this weighted indicator function, if you normalize it so that its integral is something like 1, when you integrate it against a vector satisfying this property, you'll get back, again, exactly the same vector, more or less, just by plugging in this approximation. And moreover, this operator will actually project onto vectors satisfying this property. So if you take any vector, you apply this integral operator to it, then a little change of variables in the integral, defining the integral operator, will show you that something like this property is satisfied. So we'll write omega tau for the function that achieves that projection in some approximate sense. And again, omega tau is just the function supported on group elements that you can get from multiplying together x of x when x is of this shape, or x of x when x is of that shape, and then multiplying the smooth indicator function of that subset of the group by the inverse of this eigenvalue. That's the kind of thing that omega tau is. And finally, there's a sense in which this condition determines the vectors V, and to some resolution also determines the representation pi. So there's morally something like a big O of one-dimensional space of vectors satisfying this condition, in whatever sense you can make that precise. For example, these things that we've indicated are heuristically like projections onto vectors satisfying these conditions, behave in some sense like rank one idempotent projectors. So their rank is pretty close to 1. I mean, for example, it'll grow slower than any power of t, the way we've set things up here. And yeah, idempotent means that such an operator should square back to itself. And that is not exactly what happens, but one has a relation where if you square an operator, more generally, if you compose any of these operators with any other operator of this shape, you'll get a third operator, which again has kind of the same general shape. It'll be attached to a test function that's of the same shape that we indicated. So we have some kind of heuristic proxy for the idea that we have a space of vectors microlocalized at tau, which is of dimension big O of 1. And that proxy is implemented rigorously by working systematically with the operators we get from integrating out functions of the sort I've described. So that gives a sense in which the vectors are classified by these conditions. The representations are in some sense as well, meaning if you look at the collection of representations pi for which there exist vectors satisfying this condition for a given tau, okay, that's basically the same as asking that this projector pi of omega tau onto that space be not a negligible operator. So that collection of pi that I've called F tau here is a short family in the sense of a couple slides ago. So it morally consists of some collection of representations where all the parameters, at least in generic cases, are in little windows of size roughly 1. So it'll be a family of size, something like t to the d plus 1 choose 2, or sorry, d choose 2, the way I've written it here. So, okay, these are kinds of, so as I mentioned, I mean, this whole approach to constructing vectors comes up in my paper with Akshay Venkatesh that I mentioned. It's in the abstract if you'd like to find it. So you can read more about, how we actually implement that precisely in the introductions to that paper with Venkatesh, or the second paper in the abstract. I also talk a lot about this stuff in that introduction in more detail. But okay, for today's talk, we'll just kind of use what we have here and see how, knowing that we have projections roughly of this shape with roughly these properties, can be useful for writing down integral formulas for moments of families of L functions, focusing on the example that I've indicated relevant for this bounds for standard L functions result. Are there any questions before I go on to the next slide? Okay, so if not, let's continue. So going back to this situation of this integral representation, where we had a pair of vectors in automorphic representations on a pair of neighboring general linear groups. So V is always on the big group and U is on the small group. We can ask to evaluate the size of this local integral of Whittaker functions when V and U are microlocalized. So let's write, for example, tau for the parameter at which V is microlocalized. The upper left block of tau, the upper left d by d block will be relevant. Let's call that tau 0. And let's write eta for the parameter at which U is microlocalized. So then it turns out that one can understand the sizes of these things, and it'll be roughly 0 if the sum of tau 0 and eta is not roughly 0, in some sense we make very precise, and it will be of size t to the negative d squared over 4 if that sum is close to 0. So this might look kind of small, but I mean the key feature here is that this is not, for example, exponentially small in t, which is what you'd get naively from spherical vectors. So this is actually quite a reasonable size for this integral. And yeah, I mean, kind of to zeroth approximation, you should think of the first assertion here as something like integration by parts, and the second assertion is something like stationary phase analysis. That's roughly what happens here. And so I guess this kind of result motivates looking at the collection of pairs tau and eta, which satisfy, for instance, that tau 0 plus eta is equal to 0. That algebraic condition is kind of obviously now relevant for this analysis. So in other words, since eta is just an arbitrary element of the cogent orbit of sigma, the condition says that tau 0 should have its negative lying in that cogent orbit. So suggest looking at this set here. So I've written Xi instead of tau. So we look at the set of all Xi and O pi for which negative Xi naught lies in O sigma. So such Xi will have the property that you can find a vector microlocalized at it and some microlocalized vector on the smaller group so that you have a big integral here. It turns out that this set very often behaves quite simply under conjugation by GLD of R. So that action is often simply transitive. You have any 2 points satisfying this relation can be obtained from one another by conjugation under some group element, and there's no additional symmetry. You don't have any kind of stabilizer for this action. So that tells you that there's kind of like more or less a canonical choice of elements satisfying this condition, because this group, its action doesn't really matter so much in this discussion, because you can always do a little change of variables in the integral to get rid of an element of that group. Okay. So now, how do you study moments of L functions this way? Well, given a short family of the sort in our result, consisting of pi's on the bigger group, and given some sigma on the smaller group, you can choose an element, tau, of size comparable to t that lies in your cogent orbit and has negative upper left block in the cogent orbit on the smaller group. So then the family that you're interested in is kind of forced to be the family attached to tau that's cut out by this family of integral operators. And so now if we let v pi in pi and u and sigma be the vectors that are microlocalized at tau and negative tau naught, then this kernel function that I've called k of xy, which you get by summing over rational points for PGLD, or integral points for PGLD plus 1, this is the kernel function that shows up in the pre-trace formula, for example. So we write down its spectral expansion, and I'm kind of ignoring continuous spectrum here, but that'll be okay for us. So where you sum over pi, you sum over vectors in an orthonormal basis for pi, you form the operator attached to omega tau, you act on the vector by that operator, and then you multiply by the conjugate vector. This whole sum, by the properties of these omega taus that we summarized, will first of all, within a given pi, collapse to just the microlocalized vector, because omega pi omega tau is something like a rank 1 projector with range given by the v pi's. And then moreover, the sum will, I guess, collapse, the sum over pi will collapse to your family, because outside that family, this operator is negligible. And now if you integrate this relation against the vector that's microlocalized at the complementary parameter, then plugging in the formula we had on the previous slide for the size of the local integral, you get this nice formula that says that some second moment of some family of L functions up to proportionality factor has this kind of geometric expansion in terms of integrals of automorphic forms and this automorphic kernel function. So now, of course, I mean, to say anything interesting here, you need to actually estimate this geometric integral. So we'll actually specialize further by taking our representation sigma to be the space of Eisenstein series with some complex parameter S, some d-tuple of complex numbers. And in that case, the L function that you get, this Rankin-Selberg L function, is just a product of shifted copies of the standard L function attached to pi. So for example, if you took S to be 0, you get the dth power of L of pi half. And we can find vectors that kind of live in these sigma s's, so that when S is small, we have this kind of relation. The local integral has this additional factor q to the trace of S, the sum of sj's over 2. This is the factor that kind of shows up if you want to make the functional equation look very simple. And so then when we write down some integral of Eisenstein series where we integrate effectively over S of size big O of 1, we'd really take a smooth integral with some entire rapidly decaying weight function, but I've indicated the basic shape here. Then this integral of automorphic forms ends up being something like a proxy for this sum that shows up in the approximate functional equation. So what actually happens in my paper is I estimate integrals like this, involving these wave packet Eisenstein series. But one can think of them, I mean, if you unfold an integral like this carefully enough, you get something like a sum like this after the approximate functional equation. So it's quite close in spirit to that part of an argument. And I guess the upshot is that now everything in the argument I'm about to give, in the argument in my paper, involves absolutely convergent integrals of rapidly decaying automorphic forms. So this wave packet Eisenstein series will actually decay rapidly on the quotient of GLD. And that makes life quite a bit easier. So now, summarizing the past couple of slides, we have something like a geometric formula for a T2D moment of something like a smooth dyadic sum relevant for an approximate functional equation for a standard L function on GLD plus 1, I guess. And what we need to do is we need to evaluate the right-hand side asymptotically. And we'll need to do this also for the amplified variant where we put in Heck operators. And the way that works is, well, the gamma that lie in the subgroup GLD end up contributing a main term, and that's something that is addressed using amplification. The remaining contribution we need to estimate, and we do that using two main ingredients. The first is a bit of linear algebra concerning omega tau, and the second is some kind of average growth bound for U. And the second thing comes in when we try to take into account the fact that the quotient, for the quotient is indicated here, or even the same quotient with SLD is non-compact. You have these cuspidal regions where X and Y can kind of escape off to infinity in a complicated way that'll distort the gamma that show up in this sum before they're put in as arguments to omega tau. So I'll say a little bit, I'll just say very briefly what the linear algebraic input is. It's the assertion. This is one of these linear algebra facts that I've tried to advertise as often as possible with the hope that somebody will find a different way to think about it or come up with a better proof, maybe. So it's a very elementary fact. I mean, you could pose it as a problem to any linear algebra student. It says that if you have a D plus 1 by D plus 1 matrix tau, whose upper left block I'll call tau 0, with the property that the upper left block and the original matrix have no eigenvalues in common. That's what this condition says.
A minute.
Yeah, question?
Lost connectivity, so a few slides you have missed. One or two earlier slides.
You lost connectivity. Okay. How far back should I go? I'm sorry.
You gave this. Okay. This is the next page, right now?
And then this is the next one. So should I go over this page again? Say again?
Yeah, we've seen this page. You can go to the next.
Oh, okay. Okay, maybe you haven't seen much. Okay, maybe we didn't miss too much then. So there's some linear algebra fact which says that so G here is the Lie algebra of D plus 1 dimensional matrices, H that for D. And it says that all elements X that centralize tau but are not central, and all elements Z that are central in H but not 0. So you could take Z to be 1s in the diagonal and 0 in the last entry, for example, don't satisfy this kind of commutator relation. So yeah, I don't expect anyone to kind of parse this or solve it on the spot, but it just, I mean, as you can see, it is an explicit linear algebra fact for which I don't have a very down-to-earth proof. I mean, I couldn't present the proof to a freshman linear algebra student, even though the statement is kind of clearly understandable. So I'd be happy for any feedback on that. You can see it in the second paper, at the end of the introduction of that paper, in the abstract. So this kind of quickly upgrades to some Lie group assertion involving transversality of certain varieties in the group. And since I'm short on time, I'm not going to kind of dwell on this. I'm just going to say that it upgrades to some bilinear forms estimate relevant for estimating this geometric expansion of this L function moment. So assuming that you have a couple of L2 functions on the smaller group that where one of them satisfies a bit of invariance under the center of the smaller group, and you have a group element that's not too close to the smaller group, you get a non-trivial estimate. So this turns out to be non-trivial because of the negative quarter in the exponent. If you didn't have both of these conditions, then without the 1/4, this would be a best possible estimate. You can do a bit better assuming these conditions, And the proof that you can do a bit better basically involves writing down this fact from linear algebra that you can bound the spectral radius of a matrix or of an operator in terms of the largest row sum of the matrix. And then when you actually analyze the row sums, you pretty quickly arrive at this kind of question, which then by passing to the Lie algebra boils down to this question. So this estimate you can now plug in to this right-hand side here, and it'll give some estimate that'll now kind of be in terms of local L2 norms of U. You'll kind of apply it on compact subsets of H to translates of U. And so unfortunately, because of the non-compactness of this quotient, to actually make this estimate work, you're going to need to take into account the fact that there can be arbitrarily many gamma showing up here when X and Y are close to the cusp. So for example, unipotent gamma will contribute a huge amount to this, for the same reason that unipotent elements are a complicating feature in, say, the Selberg trace formula, or more generally the Arthur trace formula for these non-compact quotients. It's the same kind of feature, but manifesting itself in a kind of a quantitative analytic way rather than an algebraic way. And so here we need one additional feature, which is a growth bound for local L2 norms of, in particular, Eisenstein series. So I've stated the bound that I ended up establishing here. So the bound is expressed in terms of reduction theory for the quotient of H. So H being GLDR, the smaller group, gamma H GLDZ. So the theory of Siegel domains says that everything in that quotient can be represented as the product of a dominant diagonal matrix that I've called A. So that's a diagonal matrix with this dominance condition, and some element X of a set that I've called omega, which is just fixed and compact. So the Haar measure on the quotient is then roughly given by taking kind of the natural Haar measure in those coordinates and dividing by this modular discriminant. If we normalize our Eisenstein series so that the L2 norm is roughly 1, then I guess that implies that when you take the local L2 norm, so you take the L2 norm on the set A omega, kind of like the part indexed by this dominant matrix A, and you divide that L2 norm by this discriminant, that quantity will be bounded by 1. We need to bound it by something actually quite a bit better than 1. I mean, the key feature here is that if either A1 is big or AD is small, then this minimum will be small. And so this dth power of the minimum will also be small. We'll get something small on this side. So the proof of that, I mean, if you had to say it in like one word, you'd say it's some kind of manifestation of Rankin-Selberg theory. We consider a Rankin-Selberg integral, well, more like a pseudo Rankin-Selberg integral attached to a test function. By choosing the test function in a sufficiently, well, there's a rather straightforward choice of a test function. It's kind of a dyadic, it's kind of like a bump function on a dyadic annulus, for which these integrals down here will bound from above expressions on the left-hand side. And then we can actually unfold this integral and try to estimate it. That'll actually end up giving one of the two estimates we need, where you take one of the alternatives in the minimum. You need one more kind of key idea, which is that when you play around with this inverse transpose map, it interchanges the two estimates you get here. So that ends up giving you the minimum, and that kind of is just barely sufficient to make the whole proof go through. So that's all I wanted to say about that argument. And I just wanted to conclude by saying that you could hope to study moments of families of L functions this way, where rather than having something like what you get from an approximate functional equation, you have an actual maybe shifted moment of L functions. So I've introduced shifts S1 through SD and T1 through TD. You can again get some kind of geometric expansion for these, as I've indicated here. There's a recipe for conjecturing main terms for moments of families of L functions that says that for this kind of moment, you expect main terms involving these products of zeta, which are indexed by all the permutations of S1 through TD. And it's pretty easy to see that you don't get such main terms from the sum that produced the main term in the earlier analysis that I've described so far for the dyadic sums. So you need to somehow find a way to combine the remaining gamma not lying in GLDZ to produce such main terms. And this is an interesting open question. So yeah, I mean, I've kind of barely started thinking about this. I exchanged some emails with Suzuki about this some months ago, and I've talked with Liang Yang at Princeton about this. you can see that the mirror-bolic subgroup, so the elements that are not just living in, say, GL2Z in this example, but also you allow the non-zero entries here to vary. Those ones, as well as their lower triangular variance, give some of the main terms you expect, but not all of them as soon as D is at least 2. The remaining contribution you expect to come from the matrices that satisfy the condition I've indicated here, where C, A inverse B vanishes, but B and C don't vanish. So you can express this group theoretically in terms of the orbit of, for example, the matrix I've written here, where I guess the key feature is that this row is orthogonal to that column. And just to give one fun example, if D is 2, one of the main terms predicted by the recipe that's not accounted for by these mirror-bolic contributions is what I've written here. And you can actually see where this comes from. So this is something we calculated. The first 2 factors come from the constant terms of the Eisenstein series. There's a standard formula for these constant terms. And the final 2 you get from some local integral that you can get by unfolding the contribution of that gamma. So I know I'm out of time, so I'm not going to dwell on that further. I'll just conclude by displaying some kind of summary again of like some of the main ideas that went into the proof of the main thing I presented. And with that, I'll thank you all for your time and attention and conclude.
Thank you, Paul, for an illuminating talk. So any questions?
Hello? Yeah.
So actually, I have 2 questions. So
Yeah, sure.
microlocal analysis is basically on Rn is the Weil calculus, right? Pseudo differential operators. So
Yeah.
where are your pseudo differential operators? Because that omega is just a function on the group. It's nothing on the cotangent bundle.
Right. So yeah, that's a good question. So yeah, so like you say, microlocal analysis in Rn is the art of working with pseudo differential operators and applying them to solve PDEs or whatever you'd like to do. Now, one way to think intuitively about what microlocal analysis achieves is think about what happens when you take the pseudo differential operator attached to some bump function in phase space. So maybe you're doing pseudo differential analysis on the real line. So your phase space is the plane. Take a little bump function up somewhere in phase space. You think of this as projecting onto something like, you know, a modulated Gaussian. That's the kind of vector you'd get out of such a bump function. Right? Like you can think of, I mean, you can think of microlocal analysis on the real line as like the art of expressing arbitrary functions in terms of functions that are microlocalized.
Localized, okay. That's
Their
okay.
support is kind of concentrated in physical space, and their frequency, their Fourier transform support is also kind of concentrated. So these vectors are kind of analogous to those coherent states or microlocalized vectors in classical microlocal analysis. The pseudo differential operators are basically the pi omega taus. And I mean, the way you think about them, which is not the perspective I've kind of emphasized here, but like, if you take omega tau and you pull it back to the Lie algebra, and then you take the Fourier transform, that'll give you a function on the dual Lie algebra that has a very, very simple shape. So for the omega taus I've indicated here, the shape is just, I should have included a picture in my talk, but it's like you take the coadjuvant orbit, which goes like this through the point tau, and you take a little thin rectangle that kind of hugs the coadjuvant orbit very tightly, but kind of spreads out along the orbit a bit. So that rectangular prism type region, if you take a bump function on that region, that is the sort of thing that is the symbol that would then project onto this vector. And so that's so the coadjuvant orbit is actually kind of the analog of phase space for these representations, the analog of like the plane for microlocal analysis in the real line. And yeah, the Fourier transform of omega tau restricted to O pi is kind of like the symbol.
So there's no problem with that. No, I'm saying, so do you pull it back to the Lie algebra because you want to use somewhere the Rossmann formula for these pi's?
So, I mean, actually okay, it depends on which paper you're asking about. If you're asking about the paper that I've kind of mainly focused on in this talk, the answer is
I'm saying in your
no.
first paper with Akshay, where you created all the machinery.
So
do you need Rossmann's formula there for the at tempered? You have a very good correspondence with coadjuvant orbits.
right. So I mean, we develop a lot of things in that paper, and some of them apply to general unitary representations, and others apply to tempered representations. So for the tempered ones, indeed, the main additional tool is the Rossmann formula. And we do apply that in my paper with Akshay Venkatesh. But for example, in this third paper I've indicated here, there's no temperedness assumption on the pi's. So the Rossmann formula is never used. And what is used instead is some kind of like analysis of the interaction of this microlocalization condition with the Whittaker model of the representation.
Okay.
And
okay.
so that's what comes in.
I wanted to ask is this. So your F tau, you define a short family that pi of omega tau is not a negligible operator.
Yeah.
So in this same vein, what is your full family that you started with?
So the full family, I mean, I guess, well, you could, so you mean like a dyadic family. So like we had short families and then dyadic families, and you're asking,
you started,
how would you cut out?
Yeah.
So how would you cut out a dyadic family? That's a good question. So basically, I mean, okay, of course, a dumb way to do it would be you just write it as a union of a bunch of short families. But a more natural answer to your question would be, let's take omega tau as I've written here, but let's kind of truncate it to a smaller neighborhood of the identity in the group. So the precise neighborhood you want to take would be something like big O of T inverse.
Okay.
You make the exponent much bigger. And if you take big O of T inverse for your omega tau, and then write down the analogous condition there, that'll define one of these dyadic families.
Okay.
It'll define kind of a dyadic ball around tau. Or I mean, more generally, you could just, rather than taking kind of a thin rectangular thing in the dual Lie algebra picture, you could take a dyadic rectangular thing, and then that'll then define a dyadic family in that sense. And those are the ones we kind of use in my paper with Akshay.
Okay. Yeah. So if you take that and then you look at all pi's such that there exists a V, which is an approximate eigenvector, right? That is right. So that's your full family in some sense.
Yep, that's right. Yeah.
Thank you.
Oh, thank you for the question. Yeah.
Yeah.
And yeah. I mean, of course, in reality, we don't work with like families. We work with like weight functions that detect families, but that's kind of a technical point. Yeah.
Hello. Yeah. So my first question is, how can you extend this to the case of number fields? Here I presume you're just working with Q, right?
Yeah. So let's address that question. So, so I mentioned very briefly this result that I have for UN plus 1 times UN for anisotropic unitary groups. So this GLN result that I've stated here, I obtained by taking the UN result. So UN is kind of like a twisted variant of GLN. You can think of GLN as like a unitary group attached to the split extension of Q rather than a non-split number field extension. So in some sense, like the GLN result is what you get by taking instead GLN and then taking one of the factors to be an Eisenstein series. So morally, if you ignore this anisotropy restriction, the GLN result is a special case of some generalization of the UN result. And now coming back to your question, the UN result is actually proved over a general number field. And there's really no reason why the GLN result that I've stated here could not be generalized to any number field. But I mean, it was more just that like, for the purpose of making the paper is going to be huge. I mean, it is huge no matter what. And like to make it as presentable and streamlined as possible, it seemed like a no-brainer to me to do it over Q, so just so the notational load is a bit lighter. Like, I mean, the natural thing you'd have over a number field would be you'd have like some finite collection of places. You could allow them to be finite places as well as infinite places. You allow your automorphic forms to be ramified heavily at those places. You put some no conductor dropping condition at those places. And then throughout the entire argument, you have some analysis that kind of applies where you have, rather than one parameter T, as I've indicated here, you have a parameter for each place, some parameter TV maybe, if V is the place. And yeah, you could absolutely run through the same argument and get the same result over a number field. But it just seemed to me that like the payoff from adding that generality and lengthening the paper more, rather than just focusing on just infinity and Q and having one place called infinity where everything happens, that seemed like a better idea to me. But I'd welcome feedback on that. If people would prefer that I write a number field version, then yeah.
Is there a periodic analog to this instead of taking GLD of R or like?
Yeah, so I mean, it doesn't exist in print in like a usable form at the moment, but yeah, I mean, well, for example, like most of the microlocal calculus stuff that I've indicated here, this works more or less the same over a p-adic field. And if in some senses, it's actually quite a bit simpler because you don't have to write approximate everywhere. You can just write equal, and you don't need to write little o. You can just write like epsilon for small enough epsilon. And this is something, I mean, if you look in my papers, I'll give some references where this is explained, but like this approach actually has like a long history in the subject of representations of p-adic groups. So it goes back to papers of Roger Howe from the 70s when he kind of kickstarted the field of like type theory, as it's now called. Yeah, so there's absolutely an analog at like a fixed prime p of everything here. It's not available off the shelf, but I mean, one could, for example, just inspect the proofs and then adapt them to the p-adic case and see what simplifies. Maybe someone will do that. And well, okay, a direction that is not kind of accounted for by this sort of calculus is the horizontal direction, where you allow the prime p to vary, and you look at things that are, say, of just level p. For that, I mean, one has typically needed some different approach or different idea, or at least the analysis is quite a bit different. It'll boil down to exponential sums analysis rather than like microlocal analysis.
Okay, thank you.
Yep, thank you.
So any other questions? If not, okay, let's thank the speaker once again. Okay.